Great. Well, thank you for that kind introduction. I'm joined here by a number of colleagues. I'll let them introduce themselves. So Noah, if you want to kick off, and then we'll go down the line here.
Dr. Noah Fitch. I am a physicist specializing in quantum sensing. In Infleqtion, I am the technical lead on the portfolio that does inertial and gravitational sensing development.
And I'm Max Perez. I am the VP of Strategic Initiatives at Infleqtion, and I'm also GMing the ticker technology portfolio.
Awesome. Jordan Sims, founding partner from Imperium Global Advisors. We support the Infleqtion team and based in Washington, D.C., and we operate primarily at the intersection of the public sector and commercial innovators like Infleqtion, with a background coming across the Nuclear Navy, the Congress, Pentagon, Department of Energy, and National Nuclear Security Agency.
Great. Well, great to be here today, and we'll get going with a few slides, and then we'll move into a Q&A session.
Thanks, Paul. So I'll kick it off. The thing that's really inspiring us to delve into the space marketplace as a near-term opportunity for quantum is basically based on the incredible growth that's projected for space hardware over the next 10 years. The U.S. Government Accountability Office, the GAO, has predicted up to 58,000 new low Earth orbit satellites by 2030, and that's of course an organization that's not really susceptible to hyperbole. Dour accountants counting satellites. This is really driven by the ability of these low Earth orbit satellites to have low latency with respect to high bandwidth communication systems for broadband internet, edge computing, autonomous systems, and is of course validated by the success of organizations like SpaceX and their Starlink product. So just the incredible volume that's potential with the space market is what's driving our interest here. In addition, there's a legacy requirement that ties economic output to the current GPS, GNSS systems. The susceptibility of that system is also driving precision products that can both harden and make that system resilient, as well as new starts in adding PNT, or position, navigation, and timing characteristics to commercial systems. And we see a huge opportunity there. So the result of an economic loss, the economic loss that's a result of a GPS outage is predicted to be $7.6 billion in the UK alone, and that's not even a trivial amount for the people over at SpaceX. So both trends, LEO satellites and GPS, are something that we're focused on. On the second slide, you show our portfolio of timing products, our ticker product line that can access that near-term market in space. The first generation targets the ground and tracking capabilities that are required to keep those satellites up there. The second generation targets the onboard systems required for position, timing for GPS upgrade paths, as well as commercial telecom. And the third generation targets really the heart and soul of that economic output, which is onboard timing systems for the lower cost LEO satellites that are really the highest growth market that we expect. With that, I'll pass it over to my colleague Noah to talk a little bit about the other side of the space marketplace for quantum.
Sure. Thanks, Max. So long before we had ambitions to put the next generation of atomic clocks in space for improved timekeeping, we've had a long history, as long as any history of any quantum company, in putting quantum hardware in space. This dates back to a program that started around 2014, the Cold Atom Lab that we did in partnership with JPL. And has had our hardware on station on the ISS since about 2017. Here on the slide, you can see evidence of that. Astronaut Christina Koch installing the module on the ISS. And we've been continuing to work with JPL and NASA on further improving these systems since then. And in fact, this week we're building new systems that will end up getting launched to the ISS late in 2025. And so what this first ever quantum lab in space really allows JPL and their investigators to do is to access, to create and study ultra-cold matter at temperatures some 1,000 times colder than what you can achieve terrestrially. So we're here talking about picokelvin temperatures. So we're talking about making atoms that are a few trillionths of a degree above absolute zero. And what that technology enables is for you to build quantum sensing architectures through atom interferometry and other approaches that really have extreme performance. Next slide, please. One of the follow-ons to developing those techniques that Cal has been a pathfinder for is a new program that NASA has started recently, seeking to put a quantum gravity gradiometer, so a device that measures quantum device that measures gravity gradients, in a standalone satellite into low Earth orbit. And this is a follow-on of some classical missions, the GRACE and GOCHI missions, which took gravitational maps of the Earth, like you see here in the slide on the top right, the false color image, which if you zoom into a particular area, lets you track things like mass distribution changes, melting ice caps, glaciers, water tables filling up in, for instance, this plot in the bottom right, California, where you can see the seasonal cycles of rainfall in California trending towards droughts, and then a particularly wet year like 2023 with the atmospheric rivers, and the entire state fills up with water and gets heavier. And you can map these things from orbit. So what a quantum version of this is going to do is to provide a much more stable, much more sensitive, and much more accurate visibility on what's happening in the planet dynamics than ever before. You can even map changes in mass distribution to seismic activity, such as the 7-pointer, which happened off the coast right next to my hometown, actually, last week. Everyone's fine, thanks for asking. And just monitoring the dynamics of the planet better than ever before, and that's what these sensors will enable us to do.
Great. So a few questions now. Maybe, Noah, we'll kick off with you. So the US and other nations have been active in space for many decades now. So clearly, we don't need quantum technologies in order to be able to utilize space, to explore space. What are the advantages that quantum brings to the space field that aren't available with classical technologies?
I think it's fair to say that we've only just dipped our toes in doing anything meaningful in space, especially venturing further from the planet. And quantum sensors offer two main advantages here. One, sensitivity. So a well-engineered quantum sensor is operating at the noise floor of nature. You can't do better than that. Two is stability. You can't, once something's in orbit, you're not going to be able to bring it back down and send it to NIST for calibration standards. The thing that you ship out to space through launch and all the things it has to go through should be your calibration standard that you bring with you. And that means it has to outperform the standards here on Earth, which we've seen cutting-edge clocks can do already, and outstrip what our standards are, and then you want to bring those standards with you. So I think stability and sensitivity to let us do things that we haven't thought of doing, and let us do things that we haven't done before. Yeah.
Very good. So we'll come back to the question of how do you actually build something like that a little bit later on. That's a fascinating question. Max, you talked about in your slides and in the session earlier about optical atomic clocks, which, if I have it right, are several orders of magnitude more precise than current timing standards. What are the implications there for GPS and how that will evolve over time? And maybe also, are there new kind of revenue streams, business model, whole businesses that might be created as a result of this new, more accurate timing standard?
Absolutely. So the heart and soul of GPS and GNSS systems is always their clock. The performance of that clock basically drives how precise the location is of the final signal on the ground. So if you do have a timing standard on board that's multiple orders of magnitude better, you can, in principle, transmit that precision down to the location on the ground. So if you're talking about precision in terms of meters today with current GPS time and frequency standards, with optical atomic clocks, higher performance systems, you're talking about sub-centimeter, potentially down to millimeter accuracy. So that opens up whole new markets like logistics chains. Imagine being able to find your keys with a little GPS receiver to the level of whether or not it's behind the coffee cup on your table or it's sitting under your couch under your cat on the couch. So that's the kind of precision we're talking about. In order to open those up in terms of new technological businesses, you actually have to introduce a whole nother layer that uses optical time transfer in order to relay the information from the GPS or the GNSS system down to the receiver. That's a technique, a time transfer technique that is only available by deploying optical atomic clocks to these space level systems. So you got new businesses, you got new infrastructure, you got new opportunities for quantum across the board for these applications.
Great. So maybe next question for you, Jordon. You mentioned in your opening remarks that you were a submarine officer in the U.S. Navy prior in your career, and we've talked a little bit about the applications of these quantum technologies for PNT, positioning, navigation, and timing. Maybe you mentioned to me earlier that there were some circumstances where you had issues with knowing your location on the surface of the Earth. So maybe you could talk a bit about that to the extent you're able to share, and then also how you might see these quantum technologies providing a solution.
They had to work really hard to find somebody that's driven around the world with no windows, so good job in finding them. But no, it's true, and there's a lot of lessons learned, I think, to unpack from. These are not far-fetched use cases, I think, is the key takeaway from this. I can speak from experience, as Paul mentioned, growing up as a young midshipman at the Naval Academy, wondering when am I ever going to use this stuff, right? To fast forwarding to being in the Western Pacific and actually answering to the name navigator every day for a professional living. We've had those issues. We've been in GPS denied environments. Submerged operations for months at a time is obviously a naturally GPS denied environment that provides kind of that extreme parallel to deep space exploration and the necessity for some of these quantum timing accuracies that Max has outlined so well. What really gets tricky is when, as any good naval nuclear propulsion program design does, is the redundancy piece, is the inertial navigation has errors along with a GPS denied environment. So that is a little bit of a pucker moment when you have to kind of resort back to your time growing up at summer camp on a wilderness survival standpoint, and how do I take a celestial fix through a periscope to relax and collapse a position of uncertainty that's growing at a fairly rapid rate so that we can make sure we're managing our risk on where that ship is. Not to mention the quantum sensing piece in terms of what that unlocks in terms of bathymetric sensing and things that we need to be very accurate and very safe with from a national mission tasking standpoint. So key takeaway from it all is we do have the lessons learned, and we are driving some of those scenarios, I think, through some of our regular DoD applications and day-to-day operations that ultimately are providing a lot of the use cases that are validating a lot of the things Max and Noah are talking about in terms of the value proposition that they provide for going a step further into the deep space exploration realm.
That's fascinating. Maybe next question, Noah, coming back to you. Here at Q2B, we kind of typically talk about quantum computing, and we talk about these enormous devices in really pristine data center environments, environmentally controlled, vibration controlled, which feels like a very different proposition from building a piece of quantum technology that we launch in a rocket that has to operate in the radiation environment of space. And then, as you mentioned before, if something goes wrong, it's not like you're going to get in a spacecraft. I don't think you've done astronaut training, at least not yet. You're not going to get in a spacecraft to go up to be able to repair it. So as a quantum physicist, as an engineer, how does that lead you to think about how you design and how you develop and how you validate these technologies so that they can fulfill these critical mission objectives?
Yeah, that one, Paul, is a very much a double-edged sword. So it's both one of the things we worry the most about in getting these things not only to survive launch, but then to operate at a very high level and at full capacity once they're in orbit or leaving the planet. On the other hand, it's also an amazing opportunity to really drive forward the engineering side of getting these quantum sensors out in the world. And historically, that's been a weak point of these quantum sensors, is they've been limited to pristine labs at controlled temperatures.
Right.
And our challenge ahead of us that we're in this industry to do is to overcome the hurdle of getting these things out in the world. Not only for space applications, but developing those same techniques and making these systems extremely robust can be turned around and be used terrestrially as well.
Fascinating. Hopefully you'll get to participate and visit at the launch of, I know you've got a couple of missions coming
I've had to promise to my wife that I'll never leave the planet, so I think a trip to the ISS is off the table.
Yeah. I think one of the things as well that we talked about offline was, unlike, say, in delivering a typical product for a customer, when you have a launch that's tied to the launch of a rocket, those dates don't move, right? So the implications are pretty significant.
That's the case for our current build for the hardware that's making its way to the ISS. They're on a schedule, they're on a budget. We have to have mature enough products to maintain and hit those schedules to support those customers, which adds another layer of difficulty and challenge, which we embrace.
So Jordon, as we're talking about government agencies here, everything we've talked about, I mean, this is a very significant undertaking, more perhaps than one organization, that any organization could do alone. How do you think about, I know you're very actively involved on the government side, how do you think about these collaborations between government and academia and private enterprise that are necessary to bring all of this to fulfillment?
Right, yeah, I think it's an important stakeholder group that has to work coherently together to make this happen. And I'm looking at it through the lens of where that public sector, private sector intersection happens. I think it's important to note, everybody here that's at an event like this plays a key role in helping, especially the public sector, larger consumption of quantum capabilities, really help to define the requirements. We see it and hear it all the time in the innovation and the venture world. Everybody talks about finding that relevant problem to solve. Translate that into the government side, it's clear requirements and the inevitable bureaucracy that comes with unpacking those requirements. So better understanding that realm of the possible. Problems beget requirements, requirements beget dollars, dollars develop the use cases, and we need those use cases to be able to actually drive kind of the de-risking effort of putting some of these into motion. And academics play a key role because they help drive a lot of those use cases, but also the R&D and some of the development efforts that keep these technologies footed in both dual use realms so that they're not just biased to the public sector or the commercial application overall. So I think that's probably the way that those need to kind of work in consortium to make a lot of this happen.
So maybe now, Max, last question for you or penultimate question for you. We talked a lot about kind of where we've been in terms of the technologies that certainly Infleqtion has developed and has either put into space or is in the process of putting into space. What are you most excited about kind of for the next, say, decade in terms of where these technologies go, what this means for our utilization of space as a resource, both from a governmental perspective and also commercially? What can we expect to see coming down the pipe here?
Yeah, absolutely. So the thing I'm most excited about the next stage of quantum technologies is getting to really volume production and deployment. So I think many of these technologies are right on the edge of going into larger volume markets, and I think space is actually a really good stepping stone in order to get there. And the reason is, generally the space market is higher value, slightly lower volume than many of the terrestrial markets that we're looking at. If you look just at the LEO constellation market, you're talking about a 10x in price point relative to the terrestrial technologies, which really kind of drives the near-term deployment of the technologies for very specific applications, simply because the dollars are there. In terms of clocks, the specific performance of the clocks that are coming out of Infleqtion right now will actually drive the types of bandwidths that are going to be required to be available through these low Earth orbit networks, and drive the type of near-term use cases in in various high bandwidth applications that are going to be take advantage of these near-term deployments. So basically, I'm just very excited about quantum taking the next step and entering these commercial markets in a very real way.
Great. Well, thank you, and thank you to my fellow panelists. I think we're at time. Thank you, everyone, for your attention, and certainly keep a lookout for what's coming in the skies from Infleqtion, and certainly we have a number of other sessions that will be talking about these technologies in much more detail over the coming days. So thank you.
Thanks, Mark.